computational model and then some computations. In fact, working with cracks, I started in problems of delamination. So that also in this I try to show you how it was created historically from my point of view. And this was considered using the theory of adhesive contact, which in fact uses some internal parameter of damage defined on the interface. That was also the reason why also for the cracks in a material there was a similar approach that made me to use the phase field approach, yeah, for the cracks inside materials. So that in my model there are various enhancements applied which were developed to the phase field model, including characterization of the parameter of the phase field model, which defines the length parameter epsilon, or including some cohesive zone model for analyzing together with phase field model. And finally, what I also want to present now is the influence of mixed mode loading on rising cracks in this approach. Well, of course, I am a man of computation, but the computation model needs some verification. So in the presentation, I'm not going to show some verification. Nevertheless, partially it was verified, or it is intended to calculate, to provide some calculations which can be compared with experiments. When I was talking about the problems of delamination, there were some experiments that show that it's in a very good agreement with standard tests that are used. And for the cracks in material, while working at the civil engineering faculty, the typical material is complete with some steel reinforcement. So it is intended that it will be used for such kind of tests. Well, not okay. So sometimes it needs more pressing. So as I said before, I want to explain the model from which is based on variational formulation. So it is can be described in terms of the energy. Standard variation model of Frankfurt-Marigo considers the energy accumulated in cracks using standard parameter GC. Well, looking at the interfaces, this is the last term within the theory of adhesive contact. In fact, we write this integral using the internal parameter zeta. Well, it is a damage-like parameter which varies between 0 and 1, but as originally it was considered as a parameter of adhesiveness. Value 1 pertains to intact state and value 0 to the full damage of crack. So it may be a bit confusing for those who work more or less with damage parameters. Nevertheless, just imagine that 1 minus zeta is zeta weight, 1 minus alpha is alpha, etc. Okay, so within the adhesive contact we have a thin adhesive layer which needs some additional energy, and in the same way it works also for the phase field model, so that the energy of the crack is regularized by a very similar function now, which is used also in the adhesive contact, and also we have the very similar form of the energy in the bulk or on the interface. Which uses some degradation function which characterizes the degradation of the material and arrangement of the actual crack. Nevertheless, when I'm talking about this description, we need to provide the unidirectional character of the crack, which can be done together together with the fact that I want to when I want to simulate the say multi-axial loading or mix type of crack, mixed mode type cracks of which may arise for various loadings. So I need some additional dissipation, which appears when the crack is in a shear mode, which may have various physical context. In the present model, it is proposed to be defined by this function, which also includes unidirectionality for the damage parameters, z7 alpha. Here we start with intact state, which is equal to 1 to 0, so that this should be the decrease of that, unlike the standard damage. Nevertheless, so what are the forms of that? Well, previously on the interface, I standardly used Hutchinson-Suo description of the GC parameter using the monicity parameter. In the similar way, it was intended to incorporate or to define the energy, which is defined by this function, and it uses orthogonal split of strain tensor to spherical and deviatory part, knowing on the fact that when we have a pure shear, then spherical part is 0, so that this will provide the energy which is proportional to GC2 minus GC1. So this is the additional dissipation to the GC1, which is in mode 1. So in this case, in such a way we have this additional energy, and we may look how this evolution of the system can be described. So in a quasi-static evolution, we may describe the solution by this system of variational relations, which are solved from the initial condition. Well, in fact, the first one is a condition of some equilibrium, and the last two are flow rules for damage, either on the interface zeta or the phase two parameter alpha. Well, in the computations rely on the convexity of epsilon with respect to each separate variable. That's the reason why I can write these relations in terms of subdifferentials. Nevertheless, in actual computational model, we used staggered time stacking algorithm, which has the advantage that the system of equation can be split, so that it's separately solved in displacements and in damage variables. And this split has the advantage that we obtain the variational structure for the solution process. It means that we have, in each time step, we have two minimizations. One with respect to the deformation quantities, and the other one with respect to the damage quantities. So it is used in the computation, and in fact the computations I want to show are some MATLAB computation with finite elements, as there is some minimization. We use quadratic programming algorithms, or generally sequential quadratic programming algorithm, if the functionals are not the quadratic, basically depending on the form of the degradation function, which appears in the function of the other one. Nevertheless, in each case, we have the minimization with some constraints defined either by the constraint applied to the damage variables, as the directionality and bounds, and due to, say, contact conditions between the domains. Okay, so now some computations with both times. Okay, so I have several calculations. Nevertheless, I rather skip this one, only going silently through the results to see how the crack is formed. So we had some animation. Well, it is rather slow computer, because usually it goes very through the time steps. On my computer it goes rapidly. So we see now the propagation of the crack. The first the crack appeared on the interface, and then something happened in the box. Okay, so again, so it's rather slow. Nevertheless, what I want to show is the mixed type loading. What happened in this case when I have lateral loading, and afterwards we see that the loading is not proportional. So first there is this lateral loading, and then the vertical. So what is changing in various situations is the domain without interface, with straight interface, and finally with a circular stiff inclusion. Okay, so first the development of the total force applied at the upper face. So we see that when I set various ratios between GCs in mode 2 or on mode 1, we see that there is no difference. Then, as we will see in the picture, the structure ruptures more or less due to shear, which may be problematic from a practical point of view. So that when it is increased, we will see that the behavior is rather different. What about the presence of the interface? Again, here we set the GCs in material to the flat value, and what can be observed, how the behavior depends on the adjustment of the GC along the interface. Again, small value, large value. Here we see that we will see that the crack appears on the interface. For this curve, we will see that the crack, in fact, is the same as there is no interface. Because the interface was not cracked. So, and finally, the same comparison for this curved interface, which represents the inclusion. So, what about the results again? So, this slow computer, and now, so we see some concentrations, and now the crack starts to appear. So, this is for the case when we have a large ratio between GC2 and GC1. And the crack here starts more or less due to maximum normal stress here, and due to this compression. And as the loading here is increased, it tends to that direction. Okay. So what happens if the ratio is equal to 1? We will see that it's more or less like in shear. Yeah? So we will see that this pressure, what happens with that. Okay, so yeah, we see that's totally different. Now the influence of the interface. The first one is with large interface GC. We see that picture is principally the same as before. And finally, we see that when we have small GC at the interface, the crack may appear actually on the interface due to loss of the passiveness in the interface. So we can check it directly on the interface because we have interface variable there. So I skip this and go to this. So this is the influence of the inclusion. Again, with small value of ratio between, there is more or less the crack like due to shear. But generally, when we increase this value, again, we can compare small value at the interface of GC, the first one, and later we will see that last picture when we have large value. So with the first one, we will see the interface crack. And the other way, we won't see the interface crack. Nevertheless, there will be some crack that appear in the material due to different material parameters of the inclusion and the matrix. So silently, I will show the movies like a century before. No sound and very slow. So yeah, so we see how the crack appeared along the interface, where the GC at the interface is small. We can also check it on the interface, looking at the variables that are defined on the interface. And finally, case of the large value of the GC at the interface, there is no crack on the interface. Nevertheless, due to various material parameters of the inclusion and matrix, there was a concentration of energy which made the phase to crack to appear there. It's in the same way as before. Again, we can see it on the interface, but there is no interface damage. Yeah, only the stress that appears that decreases because the material is exactly at the interface, but in the material of the bulk degraded. Well, I think that there were those things I want to show you how the model works with combination of phase field and interface damage. In fact, what summarizes my talk is written here that the whole process is considered as a competition between crack formation process in material and in the cracks. So thank you for your attention.
Thanks, Roman. Thanks for the presentation. So using the one-length scale, you diffuse damage in a symmetrical way around the interface.
Well, that may be similar or not, but as I said, the material of the inclusion which was used was rather stiffer, like for example, steel reinforcement in concrete. Yeah? So it has different material parameters. Nevertheless, in the case when there was the straight interface, the materials in both parts were the same. In order to see that, in fact, this interface that does not has any sense if the interface still is in a stick model. There is no interface damage.
Would it be feasible and interesting to try to adapt the diffusion length
of course
material so that depending on their property or not break the energy dissipation on both sides of the crack panel?
Yes, that's interesting.
Can you, maybe I skip it, how you do account or integrate the mode mixity in the description? Because usually in the textile model it is not. It's just a GC. And
okay,
if you want to define the mode mixity, you need to have normal and shear, and even catch around T7 or something. Just for curiosity.
Just a moment. I want to skip to. So you want to see something from the model, yes?
Yes, how the mode mixity is implemented in phase field.
You mean this one, yeah?
Or maybe the first. Yeah,
Yes,
you counted this one and then, okay, or from the previous one, I guess.
So I tried to formulate it in that way that in shear, yeah, the spherical parts of E is equal to 0, so that there will be difference between GC2 and GC1, which adds you some energy. Yeah, so proportional to that should be released, in fact, or dissipated when it is not strictly opening mode. But it just does a proposal. Well, it needs some testing. Yes, but.
Okay, you refer to the tangential and the normal with respect to the spherical and the deviatoric decomposition.
Well, all that this way, yes.
Okay, thanks. Last question.